Hey everyone, my name is Charlie Como, and this is my video lab report for the third lab, calculating the mass of a black hole. So in this lab, we're given the motion data of a star around a black hole, and are asked to calculate the mass of that black hole. The interesting thing is that we've done this before in previous labs, but the other way around, where we are given information about the object and asked to calculate data about its motion. To do so, we'll use a few physics principles: Newton's second law, Newton's universal law of gravitation, and the breakdown of forces into perpendicular and parallel components. For why this lab is worth our interest, these models and reasoning here will let us calculate the mass of any object using only its motion data, from something as large as a black hole or as small as an electron. So, to begin with, from Newton's second law, net force is equal to the change of momentum over time. As momentum is a vector, we can decompose that into its direction and magnitude. Resubstituting that back into Newton's second law allows us to apply the derivative product rule, where the first term is the component of our force parallel to, and the second is perpendicular to our object's motion. Note we can further derive our perpendicular component to the centripetal force equation. As a result, we arrive at these equations that are all mathematically equivalent. For a lab, these forces can be visually represented as shown in this free body diagram. So in our lab, we are given the positions and velocities of our star's motion. We can then yield our momentum and change of momentum over time like so. By Newton's second law, the change of momentum over time is equal to our net force. By our earlier derivation, we can yield our parallel net force component, use that to get a perpendicular net force component, and because the gravitational force is the only force acting on our star, equate our net force to Universal's law of gravitation and solve for the mass of our black hole. And this is what it all looks like coded up in GlowScript, where you can see the total, parallel, and perpendicular components of our net force as the star moves and the calculated mass printed below. After putting all these values into Excel, I found the average to be 7.83 times 10 to the 33rd kilograms, which is my final estimate for the mass of my black hole. Overall, I was pretty happy with my results, as a quick Google search found that this number is right in the neighborhood of an average black hole mass. One thing worth clarifying is that, even though they are mathematically equivalent, the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components, because the rate of change of momentum is directly measurable, whereas the net force is not. We can measure the changes in our star's speed and direction, which gives us our rate of change of momentum over time, and only through our rigorous derivation do we derive, not measure, a value for our net force. So in terms of doing this lab better again, maybe I could use the net force I calculated and see whether I could recalculate the positions of my star as the same as that I was given. And an interesting note is that if we leave the motion, mass, and position of our star the same, then by the formula we derive our black hole, it is impossible for our system to have a different mass for a black hole. Thank you.